Yeah. I think host has disabled my
हाँ,
screen sharing, it seems.
मैंने कर दिया वो भी। हाँ, करिए। अब present।
Now it is visible, sir.
Slide is visible? Okay, good, good.
Yes, sir.
Okay. So this slide you are finding in slideshow mode, or still I need to put it, convert it into slide mode. So is it fine?
Yes,
Yes,
sir.
sir.
Hello.
Yes, sir.
Yes,
Okay.
Yes, sir.
Okay.
Sir, slide mode.
Yes, sir.
Slide mode.
Okay. Okay. So good afternoon, everyone. I'm thankful to the coordinator of Academic Staff College, Dr. Pandeji. He was my senior in hostel in Rani Durgavati University when I was doing my MSc and MPhil. And Professor R.S. Chandok, he was my classmate in MPhil. So I think last time I met Dr. Pandey physically in Jabalpur, but I have not seen Professor Chandok since long. But regularly I am watching his status, and every time he is busy with some academic activities. So that's a good point that he is very well involved in academic activities. I'm happy to know and see all these activities going on at in my university, Jabalpur. So, not taking much time because I have given 1.5 hours. So, basically, before starting my lecture, I want to introduce about my institute. That is Solid State Physics Laboratory. That is a DRDO laboratory, mainly working in semiconductor materials and devices. So, basically, our mandate for the laboratory is to develop advanced semiconductor materials and convert these materials into some product. So in DRDO overall, the academic activity is more related towards ending towards some product or devices, which is useful for our defense or sometimes in space applications. So why? Because I'm involved, apart from ceramics, I'm involved in some other activities like growth of semiconductor crystals and other kind of devices. But I have chosen to talk about functional ceramics. The reason behind this, because I understand most of the participants in this course are from academic institute. And I, I hope someone must be working in the field of ceramics for their research. And even if not, I think someone will get motivated by hearing my lecture because it requires minimal infrastructure. So it's cost-effective method, very easy to adopt. So being in a small academic institute, it is better to start this activity because you need only furnace and weighing balance, some mixers. So it hardly costs around 25 lakhs rupees to start good ceramic research facility. So that's why I have chosen to talk about functional ceramics. So my talk basically will emphasize on the introduction of ceramic. What is the ceramics? Those who are well aware about the term ceramics, please excuse me, because just I want to brush up the definition of ceramics and general applications of ceramics. Then I will be covering about the technologically important ceramic material, which are basically electronic ceramics. So then electronic ceramics, then I will take one or two case studies by exploiting some principle and some material of ceramics we have converted into devices which are being used for strategic applications. So this is the full outline of my talk. So just to before starting the lecture on ceramics, I will just cover the activities which are going on in our laboratory. So basically, we are focused on making infrared focal plane array devices. So these focal plane array devices includes development of material as well as modules and final devices. So there are basically two different kind of this IR devices. One is cooled and other one is uncooled. So uncooled works at room temperature and cooled devices work at liquid nitrogen temperature, that is 77 K. So the material which is being used for cooled devices, they are basically MCT. MCT means mercury cadmium telluride. Then T2SLS. T2SLS means type 2 strained layer superlattice structures. So basically they are indium antimonide and gallium antimonide based structures. Then indium antimonide. Then we are also working on uncooled IR devices. So basically for IR sensors. So such kind of focal plane arrays devices are being used either in missile seeker or as a night vision imaging devices. So there are uncooled devices like microbolometer. So basically microbolometer works in the principle of when you heat something, there is linear change in the resistance. So that is the basic principle for bolometer. Then we are working on short wave infrared sensors also. So apart from this IR program, because this is one of the major program of our SSPL and 30% manpower is engaged in such kind of activity. Then this 30% is engaged in MMIC technology. MMIC technology, which means microwave monolithic integrated circuit. So basically using this MMIC devices, we are making amplifier. So they are basically high frequency, high power and low noise amplifier being used in radar to track the object, low lying object, high lying.
सर आवाज नहीं आ रही, नॉट ऑडिबल। हेलो। हेलो।
आवाज नहीं आ सर।
क्या हुआ?
जैसे मैं
हाँ ठीक है। ओपी सर, आप ऑडिबल नहीं हो रहे हैं। आपका माइक और वीडियो दोनों बंद है।
आई थिंक इंटरनेट इश्यूज हो रहा है।
इंटरनेट पर 1 मिनट कुछ हो गया लिखता हूँ।
यस सर, यस।
हम होंगे इसको।
हाँ, अभी तो उनका वीडियो और माइक
हेलो।
दोनों। हाँ बोलिए।
Now it's fine, sir. Video and mic both are working.
हाँ, वर्किंग वर्किंग वर्किंग।
Okay, okay, sir. Okay, okay. So, apart from this MMIC devices, we are working on laser diodes, so which are being used for detonator of explosives and laser fencing for security surveillance. And then we are working on MEMS devices, micro electromechanical systems. So basically, we are designing silicon-based accelerometer for missile seekers and other applications. So they are being used as a RF switches for high frequency. Then we are working on vector hydrophone. So we have got one group that is nanotechnology group. They are working on CNT based sensors, basically chemical sensors to sense toxic chemicals, toxic vapors. And apart from this, we are working on terahertz based imaging devices. And it's not only devices, we are working on single crystal growth of silicon carbide because nowadays, government has started semiconductor mission, this
Right.
thing, and they are putting a lot of budget on it. So several companies are eyeing on India to invest money. So now because people are using chips of silicon, and nowadays the technology is mature enough to exploit all the intrinsic and extrinsic possible advantage of silicon. So now they are exploring for some other alternate material
लेकिन
which
चीज
can withstand very high voltage, very high temperature,
पेट भोजन, हाँ ये
so
तो है।
that
और उसके साथ रस मलाई, गाजर का हलवा, कुल्फी हो जाए तो क्या कहना, मीठा सेहत के लिए अच्छा नहीं।
I think there
Background
is
wise,
आप हमारी
some noise.
बात में देना चाहते हैं।
background wise, इनका
Background noise is coming from somewhere. Okay. So now government is looking for alternate materials for silicon as a wafer so that they can make chip which can withstand very high temperature and at extreme environment. So in such cases, silicon carbide as a wafer is very potential candidate. So SSPL is also engaged in such kind of silicon carbide wafer fabrication because when you ask in large numbers for such kind of silicon carbide wafers, the European as well as American companies are denying. They thinking that you are going to use such kind of chips for strategic application. So there is need to develop such kind of wafer indigenously. That's why SSPL has taken up this project. And so far, we are able to develop silicon carbide chips of having diameter around 4-inch diameter. So we have got SSPL has got one manufacturing foundry in Hyderabad and in Bangalore. So they are productionizing the developed technology of SSPL. So we have got complete in-house facility right from material development to device development to device production. So it's our in-house facility. So just to briefly discuss, so if anybody is interested in any of this field, may contact to me so that I can connect you to the suitable scientists so that you can have a talk in your respective fields. So these are the some notable products like we have fabricated 12 gigahertz and 18 gigahertz MMIC amplifiers, so, and which are deployed in radar applications. Then we have developed laser diode, high power laser diodes. Then we are working on blue-green laser diodes also for underwater communication. Then we have developed phase shifter. So phase shifter is like a beam steering for any radar incoming signal. So phase shifter we have developed and it is being deployed in Rajendra radar. So then after this e-Nasika we have developed, and e-Nasika basically sense toxic chemicals, toxic vapors. So this is very useful even for army, even for police and for forensic lab to detect what are the toxic gases present in the environment. So it is being used for NBC application, nuclear, biological, and chemical warfare applications. And these are some thermoelectric cooler required to cool the devices. And we have developed a hydrophone for underwater communication applications. And such kind of hydrophone is has already been deployed in sonar transducer. So coming back to ceramics. So ceramic is nothing but you are routinely interacting with ceramics. Like you are taking tea in the cup, that is also ceramics. You have got earthen pot, that is also ceramic. But with time, ceramic is not only limited to earthen pot or only tea cup. Now it is advanced, being used for high-tech applications. So you will be happy to know that the origin of ceramic word came from Sanskrit word. Keramos in Sanskrit means to burn. So basically, ceramic is non-metallic inorganic materials which is being heated at very, very high temperature. Very high temperature, I mean more than 500 degrees centigrade. So it gets its strength and good mechanical properties. So that's why the burnt earthen pot or burned inorganic non-metallic material is called ceramic. So with time, the ceramic evolved from clayware, earthenware to celadon. Celadon is nothing but is kind of glazing onto the earthenware. Then we move to white porcelain, then fine ceramic. Fine ceramic, these are all capacitors, multi-layer capacitors. So made up of ceramic materials. So with time, what change we have observed is the firing temperature is increasing, the purity of the starting raw material is increasing, and compositional exactness means close control of the composition is required for high-tech ceramics. So from we are moving from pottery to electronic component. So in next slide, you will find if you see the periodic table, the light gray color elements are basically metallic elements, and this dark highlighted colors like carbon, nitrogen, oxygen, phosphorus, and sulfur, they are basically non-metallic elements. So if you make the compound by combination of metallic and non-metallic elements, so that formed compound is called ceramic. So there are wide scope because there are several element, metallic element and non-metallic elements. So if you make any sort of combination, you will get large variety of ceramic materials being used for varied applications. So if you closely look at the ceramics, so ceramic is not only uh, confined to earthenware or some porcelain, even glasses are also called ceramic. So ceramic means glasses, clay product, refractories, bricks. Bricks are also called ceramic. And you will come to know one brick which is for general purpose is being used in our home, but there are other high grades bricks which is being used in satellite. So basically these are silica based and some magnesia based refractories which can withstand very, very high temperature without deformation. So refractory has got its own field. Then we have got several abrasives like silicon carbide abrasives, alumina abrasive, boron carbide abrasives. So there are several kind of this refractory carbides and nitrides which are being used for abrasive applications. In our country, there are several companies like Saint Gobain, then Norton, Greenwell Norton, then Carborundum Universal. These companies are engaged in production of abrasives for several applications. Then cement is also under class of ceramics. Then there are advanced ceramics. So advanced ceramics means the ceramics which is being used for high-tech applications. So which include electronic ceramics. So now coming to the electronic ceramics. So electronic ceramics means the ceramics being used for electronic application. So electronic applications also include for electrical applications, magnetic applications, and optical properties. So like if you apply some electric field, you can change the refractive index so that you can change the optical properties of window material. Then if you apply some magnetic field, you can change the refractive index or dielectric constant of your material so that you can change the beam steering of incoming microwave radiations. And there are several other fields also apart from this beam steering application. In electrical application, obviously you must be knowing about piezoelectric materials, pyroelectric materials. So it has got several applications in the field of sensors and actuators. So basically, electronic ceramics are also inorganic non-metallic substances being fabricated by the implementation of very high temperature and taking the stoichiometric composition of high purity chemicals. So the key feature of electroceramics are basically they contain ionic and covalent bonding in it, and the microstructure, because all the properties are governed by microstructure and starting composition. So if you are able to control the microstructure, you are able to control the final properties. So microstructure is very important, and which consists of amorphous glassy phase in varying composition. That means the microstructure consists of crystalline phase as well as amorphous phase. So if you vary the proportion, you can vary the properties, even you can vary the mechanical strength of the final ceramic product. So these are the common applications of electroceramics, like you can use in multi-layer capacitors, you can use as a transducers, you can use as a actuators, filters in microwave devices. Then even for light igniters, gas igniters, buzzers, tweeters, you are using piezoelectric based ceramics. Then PTC sensors are there, switches are there. So there are so many applications, and if you see in the market, these are the product. So I have given the pictorial view of the final product, which is made up of ceramic material. So there are a small component, but very important in daily applications like gas sensors, pyrolytic detectors, then your metal detectors, UV detectors. So there are so many applications of this material. So if we closely look onto the definition of electroceramics, then coming to ferroelectrics, pyroelectrics, and piezoelectrics. There are three different classes of ferroelectric material. So piezo means pressure. So when you apply some pressure, there is generation of charge. That is one special class of ceramic materials, electronic ceramic material. And there is another class that is called pyroelectric materials. Pyro means fire or heat. So when you heat the material, there is generation of charge. So you can generate the charge by applying either by applying the pressure or by applying the heat. So when you apply the pressure, that means such kind of material is called piezoelectric. When you apply, give the thermal energy as an input, then it's called pyroelectric. And ferroelectricity is the subclass of these things. That means you can reverse the polarity. Like ferromagnetic material is there, similarly ferroelectric materials are there. And all these unique properties are arises because of the distinguished or very special crystal structure. So basically, when there are 32 total symmetry point groups for crystals, out of this 21 gives the non-centrosymmetric. Non-centrosymmetric, that means the positive charge and negative charge is not coinciding. That means the positive charge and negative charge is separated by certain distance. And in physics, we call this term as a dipole. So for 21 non-centrosymmetric crystal structure, there is possibility of generation of dipole. And there are 11 centrosymmetric, that means there is coincidence of positive and negative charge. That means there is no dipole. That means you cannot generate the charge on such kind of materials having centrosymmetric crystal structure. So basically, the crystal structure of the material is the main parameter which governs the final outcome of your material. So just closely looking at the piezoelectric phenomena, uh, if you apply the pressure, you can generate the charge. Even you can do vice versa. If you apply the if you apply the electric field, you can deform the material. That means you can use as an actuator. And when you apply the pressure, you can generate. That means you can use as a sensor. That means one material can be used either as a sensor or actuator. So if you are able to exploit both the properties from the single material, so that comes under the category of smart electroceramic materials or smart materials. Smart materials means the material which can sense and act accordingly to minimize the external disturbance. So that is the beauty of piezoelectric ceramic materials. And you can visualize this piezoelectricity like I told you earlier that the positive and negative charge environment is separated by certain distance that generates dipoles so that you will get the charge when you apply the pressure. So coming to pyroelectricity, if you give the thermal energy like you put the lighter in front of the material, you will get the generation of the charge. Means you will get some signal on it. So I am going to discuss the case based on pyroelectric material, and if time permits, then I will also present one case based on the piezoelectric material what we have developed in SSPL. So these are the basically materials figure of merit, because whenever you plan to develop any material, so for that, you should have some certain goals. Then to qualify whether whatever material you have synthesized is of good quality or not, that depends upon certain parameters. So these are the parameters which decides the suitability or superiority of your developed materials, like charge output coefficient that is defined by Dij. Dij means two superscripts are there, like we have got three directions, X, Y, and Z directions. So when you apply the pressure in one direction, then if you receive the signal in the same direction, then the direction is being same. So this charge coefficient is called D33. 3 means here Z direction, 2 means Y direction, and 1 means X direction. So when in piezoelectric terminology, there is one figure of merit that's called D33. D33 means charge output coefficient, means when you apply 1 Newton of pressure, then you are able to get the 1 coulomb of charge onto the surface of that material. So that D33 is 100%. So likewise, there is voltage coefficient, means the generation of output electric field per applied mechanical stress. So there are different figure of merit depends upon the application. Like voltage coefficient is useful if you develop the material for underwater application for sonar devices. D33 is useful for the material if you want to use for transducer at normal environment. And how to develop such kind of material depends upon, it's like you can make N-type silicon or P-type silicon in semiconductor. Likewise, in piezoelectric family, also you can convert into soft ceramic. Soft ceramics means N-type semiconductor. Likewise, you can think of, and hard ceramics means P-type ceramic, P-type semiconductor. So when there is soft ceramics, that means the dopant should have higher ionic radii than the host material. If the valence is less than the host material, then it will convert into hard ceramic. So this is the basic fundamental rule. So if you compare the property when you convert your material into hard or soft, the D33, that is one of the figure of merit, the value differs. For hard ceramic, the value of charge coefficient is less as compared to the soft material. Likewise, all other properties. But each material, whether it is hard material or soft material, it has got different applications. So depending upon your requirement and application, you need to put certain type of dopants. And in ferroelectric community, people generally draw this plot, dielectric constant versus temperature plot. So there are three humps you are finding on in this plot. So this plot is nothing but the transition from one crystal structure to another crystal structure. So here is the cubic structure, here is tetragonal, then orthorhombic, then rhomboidal. So when you change the crystal structure, the value of dielectric constant is also changing. So in ferroelectric community, there are different type of ferroelectric like normal ferroelectric, diffusive phase transition ferroelectric, and relaxer ferroelectric. So each class of ferroelectric has got its own merit and demerit. So because today I am talking about electronic ceramics in a polycrystalline form. Polycrystalline, that means these grains are separated by different grains with some boundary that is called grain boundary. So when we take the polycrystalline ceramics, these dipoles are randomly oriented. because this is the single grain, so it has got its unique direction of dipole moment. For this, it's a different direction. So if I put the electrode and try to extract the charge, I will not get any charge because the dipole moment direction is different. So the overall sum of all these dipoles will be zero. So at the surface of this material, I will not get any charge. So how to extract the charge from polycrystalline piezoelectric ceramics? For that, I need to do pooling. Pooling is the phenomena where we apply high DC field across the thickness of this piezoelectric material. So when I apply the high voltage DC field at higher temperature, why high temperature? Because at higher temperature, this boundary gets relatively softened. So the alignment of these dipoles becomes easier. So when I apply the DC field, this the direction of these dipoles is reversing toward the direction of the applied DC field. Because I am applying DC field onto the surface of this opposite surface of this sample. So when I apply the field at higher temperature, then while applying the DC field, I will cool the samples at room temperature. So this dipole moment direction gets switched. And when now this material has become useful because the dipoles are almost oriented because in polycrystalline ceramic it's much too impossible to align all the dipoles in a particular fashion. So the efficiency of orientation of dipole in particular direction is hardly 80 to 85%. So this is the setup where you can cool the samples. So this is the sample. This is the silicon ion bar. This is the hot plate. When you heat this sample using hot plate at higher temperature, then apply the DC power. Then you are able to orient the dipoles in particular phase. So this is the phenomena which is popularly known as the polling. And these are the factors, several factors which affect the polling phenomena. Means efficiency of orientation of dipoles for your samples. So again, it depends upon the density of your ceramics, grain shape, what is the shape, what is the size, and how the grain boundaries are distributed. Then presence of additives, whether it's hard piezoelectrics or soft piezoelectrics. Then number of polar axis directions, because again it depends upon the crystal structure, because different crystal structure has got different polar axis directions, which I will explain in this thing. Like in if you have the rhombohedral directions, then you will have 8 polar directions. That means you can align the dipoles in 8 different directions. If you have a tetragonal crystal structure, then you can align in 6 different stages. It's just like in this boundary, if you choose the composition such that the composition falls in this region, that means the composition in this region has got the coexistence of both the crystal structure, like tetragonal as well as rhombohedral. So overall, the total directions for the orientation of dipole is 6 plus 8, means 14 directions are there. It means if you get the more number of directions, then easily you can align the dipoles in particular direction. It's just like if you want to climb the stair and the gap between two stairs is very large, then you will be tired. But if there is a small step, then it's easy to climb the stairs. So the similar phenomena is there in the material also. So when we take the composition around this boundary, that is called morphotropic phase boundary, then you will find that the value gets drastically increased, like coupling coefficient, then dielectric constant is very high in this region. That's why this morphotropic phase boundary region is being exploited for piezoelectric applications. But when you talk about pyroelectric applications where you don't require high value of dielectric constant and higher value of coupling coefficient, then you have to choose the composition in this area where dielectric constant is less. One is that I am going to discuss in coming slides. So these are the basically philosophy before designing any material depending upon the applications. So how to proceed with the design of material? First, you have to do the compositional engineering, then you have to tailor the processing parameters. So when we talk about the compositional engineering, that means the final property majorly affected by the composition, starting composition, its purity, particle size of that raw material, then ionic size. What is the ionic size of the dopant and polarizability? Then type of dopant. If you want to make soft, then you have to choose another kind of element. If you want to convert into hard, then you have to choose another kind of. Then sintering aid, because density is also very important parameter. So sometimes people use liquid phase sintering or some kind of sintering aid to densify the material further. Otherwise, there will be a lot of porosity and it will be hygroscopic in nature, and you will get the dielectric breakdown. So dielectric breakdown strength will drastically degrade if you don't have something good density ceramic material. Then after compositional engineering, then you have to come for calcination temperature, then atmospheric sintering, because most of the ceramics are oxide. So when you heat at a very high temperature, so there is chances of loss of oxygen from your material. So how to compensate or adjust that oxygen losses? For that, you have to do the atmospheric sintering or atmospheric annealing in oxygen-rich atmosphere. So people are making sometimes reducing atmosphere also depending upon their use and applications. Then sintering temperature and holding time, because it also plays, because there is solid particle diffusion. So sintering temperature and time also plays very great role, and there is some diffusing, there is some diffusion length, compositional gradient, and temperature, which plays great role for the proper diffusion between two particles. And heating and cooling rate is very important, because if you cool the samples rapidly, then you will end up with the cracks in your materials, or sometimes the oxygen loss will not be recovered. So heating and cooling rate is very important. And there are different technology for powder synthesis, because to start the composition, you need to have proper control over powder shape, powder size, and particle size distribution. Otherwise, each and every time you will not get the reproducible properties. So in each and every step, you have to put a check whether your particle size is of desired range or not. If not, then do the further ball milling till you arrive to the desired particle size and particle size distribution. Otherwise, you will not get the similar kind of property at the end. So since in SSPL we have to do the scaling up of this ceramic powder, because we are initially we are developing our technology using 50-gram powder batch size, but at the final stage during technology transfer, we have to produce the ceramics in tons or maybe in kgs. So scaling up of developed technology is another challenge. And when you do something, then reproducibility, repeatability, everything is a challenge. So it takes a lot of time and you have to burn your fingers. And most of the time we learn from the failure rather than the success. So then coming to the compaction in particular shape, then we are using uniaxial press, that is popularly known as a hydraulic press. Then we are using isostatic press. So isostatic word itself shows that pressure exerted onto your ceramic article is from all around, from all the directions. So you will get good density for the final product. Then sintering. Sintering means sintering means to diffuse particles and make the final product. So there are different mechanical mechanism like conventional mechanism. That means you are using resistive furnace. But now, because it takes a lot of time and energy, so people are shifting towards microwave sintering. So even that kitchen microwave oven can be modified and used for the sintering of ceramic, but not all the ceramic can be sintered using kitchen microwave oven. It depends upon the dielectric constant and losses of your powder. Then hot pressing is another technique, but these are all costly affairs. So that's why people are using conventional method, that means resistive furnace. So these are the different processing steps to synthesize ceramic materials. So generally we start from raw materials, then we use mixers. So mixers are also different, like ball milling is there, high energy milling is there, and there are bucket milling. So there are varieties of milling machines available. Ultimately, it depends whether you want to simply mix the starting powder or you want to make the powder particle size more finer. So depending upon your requirement, you have to select the ball milling machine. Then you have to dry in the oven. Then do the calcination. Calcination is the process where this mixer is being heated at intermediate temperature, say around 800 to 1200 degrees centigrade. Again, it depends upon the starting composition. And the purpose of calcination is, sometimes it's not that for oxide ceramics, you are taking oxide as a starting material. Sometimes you take carbonates or some other form of oxide materials, starting materials. So just to evaporate carbon dioxide from the carbonate starting materials and convert into oxides, you have to do the calcination. Suppose for barium titanate, for making barium titanate ceramic, generally you start with barium carbonate and titanium oxide. So when you mix barium carbonate and titanium oxide into the proper ratio, then you heat it calcination temperature. That means you are decomposing barium carbonate into barium oxide, BaO plus CO2. That means you are eliminating CO2 from your starting chemicals. So after calcination, you have got full oxides as a material and they are partially reacted with each other. Then we do the milling, then drying, then characterization, whether what is the particle size distribution. Then you do the compaction using hydraulic press or isostatic press to convert into the form of either pellets or some other form, maybe some bar, pellets, rectangular, this thing, square shape, whatever you want. If you want to go for intricate shape, then you have to do injection molding and some other kind of this thing. So it's not that it again it depends upon the intricate shape or size of your material, what kind of compaction mechanism you have to select. Then you have to do the sintering. Sintering, that means the complete reaction between two oxides. Like in case of barium titanate, the reaction between barium oxide and TiO2. So BaO plus TiO2 is BaTiO3. So that's the way barium titanate is being formed after sintering. Then you have to cut, lap, and polish the material for final electroding. When you do the electroding, then you can do the electrical characterization like dielectric measurement, cooling, all sorts of measurement you can do. And you have to do XRD also to confirm whether the phase has been formed or not. And this is the mechanochemical alloying technique that is quite recent. It's not quite recent now. It has been since a decade. People are using. So there are different name like mechanochemical alloying. People are giving name like high energy milling. So I have used such kind of milling, mechanical chemical alloying milling, and for that I have used planetary ball mill. So in this ball mill, there are four different vials in which I put our powder and grinding media. So the impact of this grinding media on your powder is very, very high. So you will get very fine particle size, powder size. So when your particles size of your powder is very, very fine, that means reactivity is enhanced. And because of that reactivity, there is partial reaction between two constituents at room temperature itself. That's why mechanochemical alloying is very good technique to deal with high volatile constituent ceramic composition like lead oxide based constituents, bismuth oxide based constituents. So because in this process at room temperature itself, you are getting partial reaction between the constituents. So there is less chances of the losses of lead oxide as a component. So if we compare, so what I did there are several reports available in the literature, and nowadays people are made about this high energy milling, and they are trying to make nano powders because there was a um, uh, trend for nano ceramics, and also people are using to mill powders for maybe for 100 hours, 200 hours to make it finer and finer. But what I saw, when you ball mill your powder using high energy mill or planetary ball mill for longer time, then you will get the powder of fine size. But the disadvantage is you will get lot of contamination from grinding media. So what I did is I take barium titanate as a case study. Then I did the grinding for different hours, for 0 hours, half an hour, then 1.5 hours, 3 hours. So you can find the shift in the electric constant peak for this 3 hours. That means this peak shifting, because for pure barium titanate, the transition temperature is around 120 degrees centigrade. But if you induce the contamination by doing longer time ball milling, that means the zirconia is coming from your grinding media. Because I have used zirconia grinding media as a grinding ball. So that zirconia diffused into the barium titanate, and which has shifted my TC to lower temperature. So the caution from this study is that there should be optimum time for the grinding of your powder. Otherwise, you will end up with different kind of composition. You will not end up with the desired composition. And when I saw the XRD pattern for the milled powder for PLJT and the sintered powder, you may find that there is partial reaction started between the starting chemicals. That's why there is peak appearing. That shows the reaction get started at the room temperature while ball milling. So this is the grain size. I have taken photograph using SEM. So in conventional method, you can find the grain sizes are very large in size, but in high energy milling or planetary ball mill, you will get that the grain size is very fine and uniform. So when we compare the properties, that ferroelectric properties for conventionally milled powder ceramic and high energy milled powder ceramics, what we found is when we do the ferroelectric hysteresis loop, the value of remnant polarization, because this intercept will give you the remnant polarization, and this one is the spontaneous polarization. So the value of PR is increased because of this fine uniform grain size distribution, high density. And if you compare the strain means deformation in your sample. When you apply some electric field, how much deformation you get. So you will find that the even the degree of deformation is drastically increased. In the hysteresis, because I had taken deformation while increasing the electric field, while decreasing the electric field, it's following the same path. That means there is no hysteresis. That means when I make the actuator using mechanochemically processed ceramic composition, there will be less chances of heating of my devices because there is no hysteresis. So that is the advantage. And I tried to compare coupling coefficient and charge coefficient. So they are drastically increased. And I have filed the patent for this process for PLZT compositions. So now after this piezoelectric the study, now I will be talking about pyroelectric ceramic materials. So pyroelectric ceramics materials, I already described you that they are good candidates for fire detection and suppression system. I have taken this study to develop pyroelectric ceramic materials for fire detection and suppression system. So this problem was there for this Arjun tank applications because they were using this detection and suppression system imported from Japan. But later they denied to supply such kind of system to us. When we tried to develop this technology here, so I developed this fire detection systems using pyroelectric ceramic materials. What we did is to define fire, you should define that there should be flame as well as heat. If there is presence of both, like flame as well as heat, then only it will define to the fire. So I tried to put two sensors side by side, putting one filter in front of the pyroelectric detector to sense incoming radiation in the range of 0.8 to 1 micron and other 4 to 5 micron. Then I put the logic circuit for both the sensors. If there is yes signal from both the sensor, then it will give the alarm that there is fire. And according to that alarm, that suppression system, basically that is a halon tank. The nozzle of that halon tank opens when there is fire alarm. So this complete assembly is called fire detection and suppression system. For that, I tried to use modified lead zirconate titanate material. So the paralytic sensor depends upon the principle how much change is there in the spontaneous polarization with respect to temperature. So for better sensitivity, the change in the spontaneous polarization should be high. Then the detectivity of your paralytic sensor will be very, very high. So this is the schematic of pyroelectric sensor element. So what I did is I took this pyroelectric ceramic material slice. Thickness of the slice is 0.25 millimeter, means 250 micron in thickness. And there was challenge because ceramic is hard as well as brittle in nature. So if you don't end up with good quality ceramic materials and when you try to thin down the material to 250 micron, then it will get break. Or there will be porosity. So when you apply the high voltage to align the dipoles, then you will get the breakdown. So that is another challenge. So for that, you have to have very good quality materials for such kind of applications. So then I put platinum black or gold black onto the surface of it so that it can absorb more and more IR radiation coming from the object. It may be the heat or it may be something even from human being there are emission of IR radiation. So it can sense that also. So then I put this gold black paint onto the surface. Then when we ignite with IR radiation, it absorbs the IR radiation. And after IR radiation absorption, there is increase in the localized temperature of this pyrolytic ceramic material. So when there is increase in the material temperature of this material, there is the change in the spontaneous polarization. And that spontaneous polarization being arrested by putting one amplifier circuit so that you can sense in the form of signal. So this is the amplifier circuit I have connected with my sensing element. So this is the junction field effect transistor because the input resistance is very high for these samples. So and because when we talk about ferroelectric materials, they are piezoelectric in nature. So because this tank and all, they work in the field of high turbulence. There is high fluctuation of the temperature. Even there are a lot of mechanical jerk. So and so sometimes what happens, this pyroelectric sensor picks the noise from the vibrations also because they are piezoelectric in nature as apart from being pyroelectric. So how to reduce the false alarm or noise? For that, what I tried to, I put one compensating element. So what I did, I put one active element and I put another similar kind of element which is oppositely poled. So when there is vibration, so that vibration is being sensed by both the elements. Since they are connected in series and oppositely poled, so the net charge will be zero. That means there will not be any kind of false alarm. And this active element is seeing to the incoming IR radiation, while this compensating element is screened by some mechanical screens. So this is not seeing any IR radiation. So as far as IR radiation is coming, only this active element will sense. But when there is a vibration, that is sensed by both the elements. Since they are connected in series, oppositely poled, so no false alarm. That is the strategy for taking this design. And As far as this device is concerned, we have to take care of the mounting of your ceramic element, because the incoming IR radiation flux is very, very less. So the absorbed heat should be transmitted quickly throughout your sample and give the response. Otherwise, if your sample thickness is very high, then all the IR radiation will be absorbed by your element itself, and it will not transmit or it will not give any appreciable effect to sense by your amplifier circuit. So the thickness, the dimension of your material, mounting mechanism, then wiring to amplifier, all this should be taken care of very carefully. Otherwise, the detectivity and noise will be, the detectivity will be poor and your noise will be very high. So these are the different elements. So I have given the comparison between when you use different type of element or pyroelectric sensors. So this blue shaded portion, this TGS, triglycine sulfate, that is single crystal, DTGS, deuterium triglycine sulfate, this SBN, strontium, bismuth niobate, lithium tantalate. These are all these materials belongs to single crystal family. They are giving good response, but the problem is to make single crystal is another challenge. So making polycrystalline ceramic is a little easier, but making single crystal is a little bit challenging task. And for the compositional tailoring is not wide for single crystal. Whereas in ceramic, you can do lot of variation either by changing the composition or by changing the processing parameter. Then you can use PVDA polymer for pyroelectric materials, and PZT ceramic and PT ceramics. If you compare the FD is the materials figure of merit. So the for ceramic, the materials figure of merit is 4.7, whereas it is larger for the single crystal family. But that flux is very high. So you do not need very sensitive kind of sensor element, because sometimes even normal performance material will work. It depends upon your applications. So in tank application, you don't need very sensitive, because if you use such kind of single crystals, then they are hygroscopic in nature, they are brittle in nature. So there are so many other challenges. So you have to do the packaging and assembly in a different way. So that is very costly affair. Even maintaining the temperature inside the tank or some other thing, that is also very costly affair. So ceramic is quite rugged. It can sustain very high temperature, any harsh environment. So that's why it has got a lot of advantage over single crystals. So when we look for the publications related to this field, you will find that in initial days, lot of publications were based on lead-based pyroelectric ceramics. But now the trend is picking up towards lead-free pyroelectric ceramics because of the environmental concern. But still, the performance performance of lead-based material is very, very good as compared to lead-free. So there is long way to go to compete with lead-containing pyroelectrics. And if you compare the market size as far as single crystal is concerned, ceramic is concerned, thin film is concerned, and composite is concerned, you can find out from this figure that thin film is gaining market in the field of sensors. So I have already discussed about the advantage. So these are the advantage of why to take ceramic instead of single crystal. I think sufficiently I have elaborated on this point. So this is the final composition what we have taken for our current problem. So these are the application which has been already patented. So this is the final performance of our detector. That's so the materials figure of merit. This is the charge coefficient. This is the active area. This is the element size 4 mm by 5.5, even 120 micron. So, and this is the detectivity 2 into the 10 to the power 8. That is the detectivity. It is good. So, and this is the design, electrode design to uh, uh, include the compensating elements. So we have tried to use only single element and make it able to make it compensated. So there are a lot of design and other thing involved to finally come out to this design. And these are the diagram of our fabricated detectors. So these are the pyroelectric sensors developed at SSPL. So we need to put two sensors at a time side by side, one sensing the flame, other to heat. And this signal is going to your amplifier circuit and other logic circuit, which defines whether there is fire or not. So apart from this application, it has got several applications like in faucets, you might have seen this pyrolytic sensors. Then even people are using thermal, this array of this pyrolytic sensor element for thermal imaging applications. So like in hospitals, people are using such kind of imager to observe, to estimate the degree of burn in a patient. So there are some advancement. So what I was talking about, single element pyrolytic sensors, but now people have made array of pyrolytic elements which is being used for imaging applications. So these are the general applications: fire detections, intruder alarm, light switches, gas analysis, laser beam characterization, and linear arrays and focal plane arrays for thermal imaging. So now the advancement in this field is, now what people are doing, they are shifting towards the thin films or thick films. That is more supportive because the desirable thickness of your sensing element should be less, very less. So making it to in a bulk form and doing the lapping and polishing, that is another task that is time taking, and you have to consume lot of your time, hours, and money, etc. So why don't we directly go for thin film or thick film? So people are doing lot of compositional engineering and even this sample designing engineering. So what they are doing is, for pyrolytic ceramics, the dielectric constant should be very, very low. For that, what they are doing, they are putting some porous ceramic sandwiched by two dense ceramics. That will decrease your dielectric constant. So there are several different mechanisms, like in this photograph, you see they are putting reticulated kind of structure by doing some what we can etching, by etching of your top surface. So when you make such kind of cavity onto the top surface, that means you are able to absorb more and more IR. So whenever the IR radiations falls, that will be fully absorbed by the surface of your sample. So this is the another advantage. So the advantage of thin film, as I discussed earlier, like it has got small thermal time constant, high sensitivity, the dielectric constant is moderate, low tan delta, high performance, and complex integration. That means you can convert your full sensing device into the form of normal chip. So you can put it into normal package, small package. So these are the different materials that I surveyed from the literature, and most of the people are concentrating on barium strontium titanate based compositions for lead-free pyrolytic sensors. So even NASA lab, they have developed sensors and imaging array using BST. So this is the fabrication process flow of thin film based pyro sensors. So these are the device mechanisms. So first you have to deposit your PGT sole onto the silicon platinized silicon substrate. Then you have to put the carbon black or gold black onto it. Then you have to do the back etching so that this back layer is very, very thin. Then you put some IR absorption layer onto it, and when IR radiation falls into it, it is absorbed by your material and gets sensed by your electronic circuit. So these are the X-ray pattern which we did. So we tried to use laser ablation technique to deposit the PGT film onto platinized silicon substrate. So we have used purge laser deposition technique and sol gel technique for such kind of applications. So I think thank you so much for your patience hearing, and I'm very sorry that I got delayed due to some technical glitches in my laptop. So if you have got any questions, doubt, or if you want to connect in some other field, please let me know, or we can discuss right now. Time for.
Thank you, sir. हेलो
आप बोलिए।
सर, मेरा क्वेरी तो नहीं है, लेकिन जो मैंने जो देखा है आजकल
हाँ।
गोल्ड में, जो गोल्ड मेटल आ रहा है उसमें एक
हम्म।
सेरेमिक डिजाइन करके आ रहा है, तो क्या हमारी ये जो रिसर्च है इससे कोरिलेटेड वो वर्क है, या मटेरियल है, या कुछ अदर टेक्निक्स हैं वो कुछ?
कैसे कैसे सिरेमिक डिजाइन मतलब कैसे, आप कैसे रिपीट करेंगे?
जैसे मान लो कोई गोल्ड ज्वेलरी परचेज करते हैं,
हाँ 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 हाँ।
उसमें जो डोपिंग या लेयरिंग जो होती है डिजाइन की,
हम्म।
तो उसमें जब हम परचेस करते हैं तो मतलब कि सेरामिक मटेरियल से डिजाइन किया हुआ है,
अच्छा,
तो
नहीं नहीं नहीं, उसमें क्या है ना, एक तो जिरकोनिया है।
जी
एक जिरकोनिया है, और दूसरा क्या होता है, एक मर्जनाइट करके क्रिस्टल है, सेरेमिक क्रिस्टल, जो
जी
कि
जी।
सिलिकॉन कार्बाइड का बना रहता है, और उसकी जो ब्राइटनेस होती है वो डायमंड के इक्विवेलेंट है।
अच्छा अच्छा।
हाँ, वो डायमंड के इक्विवेलेंट है, वो 1/10 कॉस्ट में अवेलेबल है मार्केट में। तो कई सारे
अच्छा
लोगों को क्या हो रहा है, जो डायमंड करके वो बेच रहे हैं, वो जो आपका जो फेक वाला जो क्रिस्टल है ना, वो बेचा जा रहा है, मार्जिनाइट।
अच्छा अच्छा।
तो उसको कहते हैं मॉइजान कहते हैं, और जिरकॉन, ये इसके ट्रेड नेम है। जिरकॉन मतलब जिरकोनिया क्रिस्टल है, और
जी जी
मॉइजनाइट मतलब सिलिकॉन कार्बाइड का क्रिस्टल है।
जी
तो उसमें क्या होता है, उसका सिंगल क्रिस्टल बनाते हैं तो बल्क के फॉर्म में बन जाता है। और उसको
जी
फिर
जी।
क्या करते हैं ये लोग, बेसिकली चाइना और कोरिया से, गुजरात में इंपोर्ट होता है। तो बाकी
जी
वो
जी।
डायमंड की उनके पास में पूरी प्रोसेसिंग, सेम प्रोसेसिंग अडॉप्ट करके वो डायमंड ज्वेलरी के जैसे, अनटिल
ओके।
अनलेस आप उसका रिफ्लेक्टिव इंडेक्स लैब में मेजर करेंगे, आपको पता नहीं लगेगा विच वन इज डायमंड, विच वन इज मर्सराइट।
जी
तो ये आजकल मार्केट में बहुत काफी कुछ हो रहा है। और हर एक आदमी रिफ्रैक्टिव इंडेक्स तो मेजर करेगा नहीं।
जी 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 जी
हाँ, तो ये तो चल रहा है, ये चल रहा
जी।
है।
अच्छा, दूसरा मेरा एक प्रश्न था सर, कि जैसे
हम्म।
आपने सोल्जर टेक्निक्स की जिक्र किया था,
हाँ
तो
हाँ।
इसके इसके अलावा जैसे मान लो सॉलिड स्टेट मेथड अगर ऑप्ट करते हैं, क्योंकि हम लोग रूरल बैकग्राउंड में काम करते हैं,
कोई बात नहीं, ठीक है।
तो क्या? यस सर।
हाँ हाँ, नहीं ठीक है, आप बोलिए।
तो रूरल बैकग्राउंड में जब हम सॉलिड स्टेट मेथड अगर ऑप्ट करते हैं, तो
हम्म।
सैंपल का जब प्योरिटी है, या यूँ बात करें कि हम डोपिंग करते हैं,
हम्म।
डोपिंग करेंगे, तो डोपिंग करने के बाद उसका कैरेक्टराइजेशन का प्योरिटी की पॉसिबिलिटी कैसी क्या रहेगी?
देखिए, अब वो डिपेंड करता है कि कितनी इम्प्योरिटी उसमें है। ठीक है।
जी जी
यदि इम्प्योरिटी बहुत ज्यादा है तो ईडीएक्स टेक्निक से पता लग जाएगा, जो सैन के साथ में ईडीएक्स होता है ना,
जी जी जी
स्कैनिंग इलेक्ट्रॉन माइक्रोस्कोप,
जी।
माइक्रोस्कोपी के साथ में एक ईडीएक्स आता है। ठीक है।
अच्छा। जी जी
इलेक्ट्रॉन डिस्पर्सिव एक्सरे एनालिसिस, ठीक है,
जी जी
ईडीएएक्स। ठीक है। इलेक्ट्रॉन
जी जी
डिफ्रेक्शन, ठीक है, एनालिसिस ऑफ बाई एक्सरे, ठीक है।
जी।
तो
ओके।
उससे पता लग जाता है। और यदि उससे कम यदि इम्प्योरिटी रही तो आपको ईपीएमए एक आता है, इलेक्ट्रॉन प्रोब माइक्रो एनालिसिस।
जी जी
और यदि उससे भी नहीं पता लगता है तो आते हैं आईसीपी,
जी
इंडक्टिव कपल्ड प्लाज्मा मास स्पेक्ट्रोस्कोपी। ठीक है।
जी
एक
जी।
होता है टाइम ऑफ फ्लाइट मेजरमेंट, होता है सिम्स,
से
सेकेंडरी आयन मास स्पेक्ट्रोस्कोपी।
ओके।
ठीक है। और यदि बहुत कम है, पीपीएम लेवल पे है या पीपीबी लेवल, पीपीएम लेवल पे, तो
जी
उसके
जी
लिए आता है जीडीएमएस, ग्लो
जी।
डिस्चार्ज मास स्पेक्ट्रोस्कोपी, जो इंडिया में अवेलेबल नहीं है।
ओके।
हाँ, इसके लिए आपको यूएस या फ्रांस की हेल्प लेनी पड़ेगी, वो पेमेंट बेसिस पे करते हैं। बट आपको, मुझे
अच्छा।
नहीं लगता है कि इतने लेवल पे जाना पड़ेगा। उसका
जी जी
रीजन ये है, क्योंकि आप जो भी मटेरियल खरीद रहे हैं उसकी प्योरिटी क्या है।
जी। हाँ,
तो
इसका भी
उसकी
एक स्टैंडर्ड रहता है कि ये इसी स्टैंडर्ड का होगा तो आप कुछ ठीक से रिजल्ट मिल सकते हैं जब
देखो,
मार्केट में जब परचेस करते हैं हम लोग।
3 and 5 इज मोर देन सफिशिएंट, 99.95।
ओके।
हम्म। AR grade 99.95 is more than sufficient सिरेमिक
ओके
एप्लीकेशन के लिए। यदि आपको
जी
सेमी
जी
कंडक्टर में जाना है तब तो 6N चाहिए। 6N
ओके
मीन्स 99.9999,
ओके
6 बार 9 है ना,
जी जी
99 के
जी
बाद में तो वो डिपेंड करता
थैंक यू
है। सिरेमिक में
थैंक
आपको
यू
बहुत ज्यादा, क्योंकि देखो जब बहुत हाई प्योरिटी का एक मटेरियल ले लिया और दूसरा कम ले लिया तो आप पैसा
जी
वेस्ट कर रहे हैं अपना। ठीक है,
जी जी जी
कोई फायदा नहीं। या तो सभी हो हाई प्योरिटी के, फिर उसके लिए इन्वायरमेंट भी क्लीन रूम हो आपके पास में,
जी जी
है ना। आपने मटेरियल तो ले लिया हाई प्योरिटी का और उसको ओपन में खोल दिया तो हाई प्योरिटी रहा नहीं।
जी जी जी
क्योंकि मटेरियल क्या, जितना हाईली प्योर होगा वो एक्सपोज भी बहुत जल्दी होता है।
जी
हम्म, है ना? तो
ओके
आपको
थैंक
थ्री
यू
एंड फाइव से ज्यादा की जरूरत नहीं है,
जी
उसमें काम हो जाएगा आपको। ठीक है,
थैंक यू सर वंडरफुल सेशन
ओके।
Thank you,
और
sir.
कोई हेल्प चाहिए
Thank you, sir.
कैरेक्टराइजेशन में, प्लीज लेट मी
यस सर या डेफिनेटली सर
नो।
और कोई? कृणाल,
Yes, sir. Yes, sir.
चलिए सर को थैंक्स गिविंग बोल
जी सर,
दीजिए।
जी सर। So on behalf of MM-TTC IDVV Jabalpur, I thank Dr. O.P. Thakur sir for giving such a wonderful lecture and giving such a precious information regarding ceramics. And so at the end of this session, from all of our participants and on behalf of MMTTC, I thank Dr. O.P. Thakur sir, and with the permission of chair and with Dr. Pandey sir's permission, I declare here that this session is over.